Hey guys, Mr. Smith here, and in this video lesson, we're going to be learning about the factor theorem. We're also going to learn another method for dividing polynomials that some of you may prefer to use moving forward, something called synthetic division. But our starting point for today is, and we briefly mentioned it in the last video lesson. Um, our last lesson was about the remainder theorem. And the remainder theorem said this. So when you divide a polynomial by a binomial of the form x minus b, the remainder is the value of that function at b. We also had a little extension of that. When you divide by a binomial where the leading coefficient isn't 1, ax minus b, the remainder is the value of the function evaluated at b over a. Essentially, whatever makes that factor ax minus b equal to 0. A consequence of this, and what it leads to, is the factor theorem. If a binomial is a factor of a polynomial, it means we should get a remainder of 0 when you divide them. And this is what the factor theorem says. That a factor, binomial factor x minus b, is a factor of a polynomial if and only if the value of the function, that polynomial at b, is 0. And in a similar way, ax minus b will be a factor if the value of the function evaluated at b over a is equal to 0. So this is actually, it's really just the remainder theorem, but we're considering the case when the remainder is 0. That means that we have a factor. Now this math, I just have you can copy this down or not, but that math terminology, if and only if, means those statements work both ways. So that statement, that top statement is saying, okay, so if x minus b is a factor, then p at b is equal to 0. So for example, if you have a polynomial where, like, say, x minus 2 is a factor, that means that the value of the function at 2 is equal to 0. But it works the other way too. So let's say that you plug 4 into the polynomial function and you get 0, then right away that you can conclude that x minus 4 is a factor. So it works both ways. And that'll be very useful for us as we try to factor larger and larger polynomials. Let's continue. So we're going to apply the factor theorem. We're going to start off by just playing around the factor theorem and doing a bit of work by hand. But then I'm also going to show you guys how you can use technology, because just doing things by hand can be a bit tedious. And for certain things, we want to make use of calculators and technology to help us out. So here's our polynomial. 2x cubed plus 3x squared minus 3x minus 2. Maybe I'll even just toss in here. Let's let p of x be that polynomial function. So if we want to know if x minus 2 is a factor of that polynomial, then we just need to evaluate the value of the function at 2. And so we'll slam this out here. So I'm going to do just the first 2 of these by hand, and then allow you guys some time to try the rest on your own. And then we'll make more use of technology throughout the rest of the lesson. So what do we get? Well, tablet acting up on me. All right, what do we get? So that first term will be 16 plus 3 times 2 squared is 12, minus 6 minus 2, 28 minus 8, that's 20. So we don't get 0, and so x minus 2, certainly not a factor. Let's try evaluating at negative 2. 2 times negative 2 cubed plus 3 times negative 2 squared minus 3 times negative 2 minus 2. So that'll be negative 16 plus 12 plus 6 minus 2. Now that works out to 0. And so we automatically know that x plus 2, what am I writing that in? That yes, that is a factor. It is a factor. Which is good for us. It means that when we divide that polynomial by x plus 2, we'll get a remainder of 0. We can actually start factoring that larger polynomial, which we'll do shortly. What I'd like you guys to do, can you try these last three, especially the last one? What would you plug into that polynomial to see if 2x plus 1 is indeed a function? So I'm going to pause my recording and do these. I would be great if you pause your video lesson and try these too, and then you can unpause when you're ready. I'll see you guys in a second. All right, guys, hopefully you gave those a go, and here are my results. Here are my results. There we go. Turn the screen to the program. So when I plugged in negative 1, I got a remainder of 2, not a factor. When I plugged in 1, I got 0. X minus 1 is a factor. When I plugged in negative 1/2, that is the value of x that makes 2x plus 1 0. I got 0 as well. And a really neat thing is that what we've seen, we actually have 3 linear factors: 2x plus 1, x minus 1, and x plus 2. We actually know how to factor this polynomial. This polynomial, I'm just improvising on the fly here. Wasn't planning on doing this, but I think it's a good talking point. This polynomial we were working with, we now know how to factor it, right? What did we find was a factor? X plus 2 was a factor. X minus 1 was a factor. And 2x plus 1 was a factor as well. We have factored that polynomial. Now, plug and play and doing things by hand can be a bit tedious. So let me show you how we can use a program like Desmos to do this work for us. So I have Desmos loaded up here. And so what we do when you're in Desmos, we want to define that polynomial function that we're working with. So for us, it was p of x equals 2x cubed minus 2, I think it was minus 2x squared, plus 3x squared, plus 3x squared, plus 3x squared, minus 3x, oh, my memory is terrible, minus 3x minus 2. And then below that, we're going to add a table. And we want, given certain x values, and the x values we were testing were 2, negative 2, 1, negative 1, 1, and negative 1/2. So you pop those in. So 2, negative 2, and we did negative 1, 1, and negative 1/2. And we want Desmos to do the plugging in for us. And so in this column here, you just type, the polynomial p of x. We just do p of x1, and then it's just going to use the values defined in the column x1. And you can see we get the same values that we got earlier. Minus 2, 1, and minus 1/2 give us 0. They were factors. Also confirmed on the graph, these are the zeros of this cubic function. So when you guys are doing practice, when you guys are doing an assignment, it's having this technology open will be helpful to you. There are going to be times where I might want you to, verify that x minus 2 is a factor of this polynomial by applying the factor theorem, and I want you to show your work. I want you to convince me that you understand how to apply this. But, if we're doing, tens of these as we practice, it's much more convenient to have a calculator to check those for us. So I'm going to keep Desmos open here because we might come back to it and do some more stuff like this as we factor big polynomials. So let's head back. All right. So let's do an example. So here's another cubic polynomial, and we're going to fully factor it. We're going to use the factor theorem, and yeah, it's going to be good. Now, I do have a tip for you guys. You know, in the previous question, I gave you some values to try, right? We tried 2, -2, 1, -1, -1/2. I'm not sure if you would have thought to try -1/2 on your own. But like, what values, you know, if I'm looking for factors, how do we decide what kind of values to plug in and look for a remainder of 0? So this is where the integral 0 theorem comes in. So this is just a helpful tip for you guys. So I'm going to have it there. So on the space here to the left, I'm going to kind of develop a little tip for you guys here. So I'll just say tip. I think that's on your sheet. But like, let's say that we have some binomial factor, x minus b is a factor, right? Then we know that when you plug in b, you get 0. And so for our case here, we would get b cubed plus 2x squared minus 5x minus 6 equals 0. Oh, I forgot to plug in the b's. You have to forgive me for that. That should be 2b squared minus 5b minus 6 equals 0. And I'm going to do a little bit of massaging this expression here. That would give us, I'm going to move the constant term to the right, actually. 5b equals 6. And I'm going to common factor out the b, and we'll talk about why in a second. B squared plus 2b minus 5 equals 6. All right. So if b is going to be like a 0 of this polynomial, then whatever b is, and b is an integer, if b is an integer, then b squared, b is an integer, I'll just say that. If b is an integer, and well, then b squared plus 2b minus 5 will also be an integer, and those two things multiply to 6. Guys, this is the key. If we're looking for possible factors, looking for possible roots, possible values for b, we don't have to just randomly guess. What must happen here is that our choices for b have to be factors of 6. Could be positive or -1, positive or -2, positive or -3, or positive or -6. It has to be that way. That's the only way that this expression can give you a product of 6. And so that will give us some starting points into looking for factors. And this kind of tip can be summarized as the integral 0 theorem. And it works when you're working with polynomials with a leading coefficient of 1. Of course, the coefficients have to be integers too. So if x minus b is a factor of a polynomial function, then b is a factor of the constant term, right? So for when we're doing our question here, we're looking for factors, but we know the factors will either be x plus 1, x minus 1, x plus 2, x minus 2, x plus 3, x minus 3, or x plus 1, or x plus 6, x minus 6. They have to be factors of the constant term 6. So having done that, let's apply our integral 0 theorem. So what we want to check is different values of x until we find a factor. So we have to check plus or minus 1, plus or minus 2, plus or minus 3, or plus or minus 6. And until, and why those? Because all those numbers, those are factors of the constant term 6, right? So usually we start easy. and then just work your way up until you find something that works. Now, I'm going to bring back Desmos here. I think that makes sense for us to do. Desmos, just to save us some time. So I'm going to just, clear things out and then update my polynomial, the one that we're working with. And which guy are we working with here? We are doing x squared plus 2x squared minus 5x minus 6. All right, and let's start checking some values. Whoops, don't want that. Add a table. I guess be consistent, I'll put it underneath. What am I even doing here? Add a table. We're gonna try, let's try 1 and -1 to start. And we're plugging them into our polynomial p. All right, so -8 and 2. So those are not factors. Did I punch in the right one? X? No, I didn't. That should be cubed. Okay, there we go. So 1 isn't a factor, but -1 is. P at -1 is equal to 0. So we've found a factor. So I'm going to head back to our note. So I'm just going to add a little note from Desmos. We found that P at, was it 1 or -1? -1 equals 0, which means that x plus 1 is a factor. And we can continue on now, since we know x plus 1 is a factor, we can now factor this expression. We're now going to use division. So let's divide. Let's see what we get when we divide x plus 1 into x cubed plus 2x squared minus 5x minus 6. Now we know the remainder is going to be 0, right? The only question left is, like, with what we get left over, will that be able to be factored as well? So x into x cubed, x squared, multiply x cubed plus x squared. Move a little bit faster since we practiced lots of this in our last lesson. Then we subtract x squared. X goes into x squared x times. And then, forgot to bring down my minus 5x. Multiply x squared plus x. And now we subtract. -5 subtract 1, -6x. Bring this down, minus 6. This is looking good, guys. X goes into -6x minus 6 times, and we do get a remainder of 0, which is what we knew would happen, right? If that didn't happen, go back and check. We made a mistake. So what have we shown here? And we wrote statements like this out in our last lesson. What we have shown is that this polynomial function, p of x, x cubed plus 2x squared minus 5x minus 6 is equal to x plus 1 times x squared plus x minus 6. We've kind of factored it. Very cool. And now we ask ourselves, can we go even further? And we can. That simple trinomial, x squared plus x minus 6, can be factored as x plus 3 times x minus 2. Those are also factors. And in fact, guys, and we'll check on Desmos, if we had kept going and checked all of these values, we would have seen that -3 and 2 also give us a remainder of 0. And we can just kind of check this out. -3 gives us 0, and 2 also gives us 0. Now, I do want to say this, is that, like, with technology, we could have easily checked all 8 of these possibilities, found the 3 that work, and went right to our factored form, which is, like, okay if you just need it to be factored so you can do something else. But we want you guys to kind of develop this skill and really understand the nuts and bolts of the factor theorem and division. So I would like to see you guys find a factor and then apply division. We want to make sure you guys have these skills. Ultimately, like once you've get really comfortable and you feel you're proficient at this, yeah, if your ultimate goal is just to factor a polynomial so you can do more important things, of course you would like to use technology to do that. But really want to reinforce here, guys. This is my expectation. This is the process I'd like you guys to be able to do. Of course, technology is great as a check right now. All right. Yeah, that was fun. Let's continue. At this point, we've done a lot of long division, and you may not prefer it. You might find it takes a long time. You have a hard time maybe keeping track of negatives, doing the subtraction, or whatever reason. There is another method or a system of division that it applies the same ideas as long division, but it kind of streamlines it into an algorithm that just works. And on the surface, you might not understand why it works, but the machinery behind the scenes, it's just doing those long division processes for us. So I'm going to show you guys how we can do synthetic division for our previous to do our previous problem. So we're going to divide our polynomial x, the one we worked with before, x cubed plus 2x squared minus 5x minus 6. And we're going to do something called synthetic division. Now, the first thing to notice with this table we set up here, this division chart, the minus 2 is actually just the number. You see how it's x minus 2, and we just plug in minus 2. Minus 2 goes up here. And then here we have the coefficients of our polynomial. 1, 2, minus 5, 6, right? 1, 2, minus 5, and 6. So that's what we set up. We have a minus sign here because we're going to be doing some subtracting, and a multiplication sign here as a prompt to do some multiplying. And so here's how this method works. And it's just an algorithm, and it just works, guys. So you set it up. What do? You start with the leading coefficient, and you just bring it down. 1. Next, you multiply negative 2 times 1, and you get negative 2. Then you subtract. That's what this prompt here, this negative here is. It's prompting you to subtract. 2 subtract 2, or 2 subtract negative 2 is positive 4. And then we multiply negative 2 by 4, negative 8. And then we subtract. Negative 5, take away negative 8 is positive 3. And then we multiply again. Negative 2 times positive 3 is negative 6. And we subtract, and we get 0. Now, what are these numbers on the bottom means is these numbers correspond to the coefficients of our quotient, x squared plus 4x plus 3. And the 0 is what we wanted. It shows you that you get remainder 0. Because we already knew that x minus 2 is a factor already. This is what was expected. And what this means is that we can write our polynomial as x minus 2. It is a factor. And what's left over when you divide that out is x squared plus 4x plus 3, which you can factor some more. X squared plus 4x plus 3, it's a simple trinomial, factors of x plus 1, x plus 3. And we get the same fully factored form from the previous method, right? X plus 1, x plus 3, x minus 2. Here, they're just in a different order. Synthetic division, there's pros and cons. On the plus side, it's quicker. It's an algorithm that you just apply the same process every time. The downside, I would say the downside is as you're using this method, it's hard to see the why of why it works. Long division is great in my opinion because you can see how everything is working. This is just a, hey, it works, trust us kind of thing. But you now have a second tool. Let's actually try a couple more. let's use synthetic division to do these polynomial divisions, and we're not going to take these to completion in terms of fully factoring. We're just going to practice our synthetic division. So we set up our synthetic division table. We're dividing by x plus 1, which means we put plus 1 here, and you can add in if you'd like. You're subtracting and multiplying prompts. And then you write down the leading coefficients: 1, 2, -1, 5, and 7. And I'll just switch to a different color. As usual, guys, if you feel like you want to try it on your own, why can't I get my different color? Please try it on your own. If you'd feel more comfortable just doing it with me, that's great. And then maybe you can try the next one on your own. Let's apply our algorithm. We bring down the 1, and then we multiply. 1 times 1 is 1. 2 minus 1 is 1. And we multiply. 1 times 1 is 1. -1 subtract 1 is -2. We multiply. 1 times -2 is -2. 5 subtract -2 is 7. 1 times 7 is 7. And we subtract, we get 0. So what we have shown, first of all, we have shown that this division equals x cubed. Remember, these resulting numbers are the coefficients of our quotient. X cubed plus x squared minus 2x plus 7. If we were trying to factor it, copy this down or not, it's as you'd like. But what we have shown is that, if we were trying to factor that huge quartic polynomial expression, well, we've got off to a start. This is equal to x plus 1 times x cubed plus x squared minus 2x plus 7. And if you wanted to keep factoring, you could now apply the factor theorem to this resulting cubic expression, try to find a factor, and keep going and keep going. Let's try the next one. I'd really encourage you to pause the video and just try it yourself. There is actually kind of a twist to this one. You'll notice that the dividend doesn't have a linear term. So how do we deal with that? So setting our table up, we're dividing by x minus 2, so we need minus 2 there in our prompts. And then we write down the coefficients, but you have to include 2 minus 1. You have to include a placeholder when there's no term. So placeholder 0. And then go for it. Now, you may prefer to add the arrows in as you go, but for me, I can find it a bit clunky. So when I'm doing these, so I'm just going to apply the method now. So bring down the 2. -2 times 2 is -4. I subtract these, I get positive 3. I multiply, I get -6. I subtract 0, take away -6, I get positive 6. I multiply, I get -12. And I subtract those, I get 0. And so what we have seen, I regret writing that there, what we have seen is that this division is equal to 2x squared plus 3x plus 6. Or in other words, this cubic polynomial expression, we could factor it as x minus 2 times 2x squared plus 3x plus 6. If you're wondering why all the big deal about why is it necessary to factor these, well, from your grade 10 course, we have mentioned factoring can be a useful skill in solving equations, and especially solving polynomial equations. It's going to help us find solutions. It can be very useful. So that's synthetic division. Now, moving forward, you can use long division or synthetic division. It doesn't matter to me, but I might start using synthetic division a bit more as we do some work, just because it is a little bit faster. But both methods work, and it's just personal choice. Okay, so we introduced synthetic division. We gave it a couple goes, got some examples in our notes. I definitely encourage you to try to practice synthetic division later in combination with long division. But let's continue. So we're going to factor another polynomial, and we're going to combine our factor theorem with other methods from earlier grades. Now, our starting point here is we just have to use the factor theorem, and we have to um, find a factor. And remember, we don't have to randomly choose what to try. If we look at, so this is a polynomial, its leading coefficient is 1. We look at the constant term, negative 18. So think about the number 18 and what are the factors of 18? Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, and plus or minus 18. So let's open up a graphing program. I'll use Desmos, and let's try some of these values until we find a factor. I might pause the video and get that set up. All right, guys, so I got a hit right off the bat. In Desmos, I entered my polynomial, and I start with -1, and I got a hit. I do want to stress, from this graph, we can actually see that we get zeros at -3, -2, -1, and 3. So we know our factors already. The purpose of, but I want to continue to do some factoring by hand and understand the methods and not just use technology to spit out the answers at us. But so at the end, when we're finished this question, we'll come back to the graph and just see this makes sense. But so that's kind of going to be my starting point. X plus 1 is a factor. Let's continue. There we go. So step 1, I'll switch back to my navy blue. Complete. We used a technology to show that p at -1 was equal to 0. And so x plus 1, I don't know why I keep writing the brackets there. X plus 1 is a factor. Let's use synthetic division this time. So x plus 1 is a factor. I write down plus 1 and set up my prompts. Write down the leading coefficients, 1, 3, -7, -27, -18. And then I start applying synthetic division, this little algorithm. Bring down the 1. 1 times 1 is 1. 3 minus 1 is 2. 1 times 2 is 2. -7 minus 2 is -9. 1 times -9 is -9. -27 take away -9. -18. Multiply -18. And I subtract those, I get 0. A self-check. We knew we had to get a remainder of 0. And so what did this show us? This showed us that our polynomial, p of x, x fourth plus 3x cubed minus 7x squared minus 27x minus 18 is equal to x plus 1 times, and our synthetic division shows us it's x cubed plus 2x squared minus 9x minus 18. All right, now we have some options. Our two options are, well, our first one of our options is to take the cubic polynomial in that second bracket and apply the factor theorem and do more division. Or we could apply some factoring techniques from earlier grades. So we're going to do both. I'm just going to recopy this down. You guys don't need to because it's on you have a lesson sheet, but I need to transfer it from slide to slide. X cubed plus 2x squared minus 9x minus 18. So this cubic polynomial expression has 4 terms. 4-term expressions are a candidate for group factoring. If you can notice that you can pair them up. In this case, we can actually. Let's see how this works. So I'm going to leave my factor of x plus 1 out there. Might just pop in some square brackets here, but the first 2 terms have an x in common. Actually, they have x squared in common. And when you common factor the first 2 terms, you get x plus 2. When you common factor the last 2 terms, minus 9, you also get x plus 2. And that x plus 2 is a common binomial factor. And when you remove it from those 2 terms, you're left with x squared, you're left with minus 9. And we can keep going. X squared minus 9 is a difference of squares, and it factors to x minus 3, x plus 3. And we've fully factored our polynomial. So the idea here is, guys, like we don't have to fully rely on the factor theorem and long division or synthetic division. Sometimes the techniques we've already learned can help us, and in my opinion, this was very quick and efficient. I also want to point out, check out the graph. So this is saying our graph will have zeros at -1, -2, -3, and 3, and that is exactly what we found out from Desmos, right? Everything lines up. Having a graphing program open is not cheating. It's useful for checking answers and stuff. But again, guys, I don't want to rely on technology for everything. I want to make sure you guys have the skills of these underlying methods. So that's option one. Option two is continue using the factor theorem and division. So what I'm going to do is I'm just going to call that leftover cubic polynomial, which was x cubed plus 2x squared minus 9x minus 18. Like, let's say we didn't recognize that we could use group factoring, so we have to rely on our other methods. So what are the factors we can try? Again, look at the constant term. We're going to try plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, plus or minus 18. Now, you guys, we already know, right, from our previous work, let's say x plus 2 is a factor. So we already know that when we plug in minus 2, we're going to get 0, and that x plus 2 is a factor. I keep writing the brackets. That's okay. X plus 2 is a factor of q at x. In practice, you guys would test those values, maybe use Desmos until you discovered that fact, okay? Yeah, let's use synthetic division again and see what we get when we divide this cubic guy, 1, 2, minus 9, minus 18. Set up our prompts, and here we go. Bring down the 1. 2 times 1 is 2. 2 minus 2 is 0. 2 times 0 is 0. Minus 9 minus 0 is minus 9. 2 times minus 9 is minus 18. And then we get a 0, which we expected. What do these coefficients correspond to? What we have just shown, guys, is that function q, x plus 2 was a factor of it, and we got x squared minus 9. Things are looking familiar. So putting everything together, p at x was x plus 1 times our cubic guy, x cubed. I'm kind of rewriting this because I just reinforce some things. And we just showed that x plus 2, that cubic expression can be written as x plus 2 times x squared minus 9. And of course, like before, we can difference of squares factor that last bit, and we get the same answer. Factoring or grouping, definitely more efficient, but you guys get the idea here, is that once you remove a factor and get a lower degree remaining factor, you can keep applying this method down and down and down and down until you have something fully factored. So you have two methods. Apply other strategies from earlier grades, but the factor theorem and division will always help. Again, guys, I know the technology would have given us this answer right off the top because we can see the zeros, but I don't want you guys just to get good using Desmos to get answers. I want you guys to be able to apply the factor theorem, use long division. All right, guys, we're doing great. One more example to do. It's an application example similar to one we've done before, but this time I want to, but we haven't actually done any examples where the leading coefficient is not 1. So I want to give you guys tips for how to look for factors in situations like this, because our integral zero theorem doesn't apply for these kind of cases. So here we go. Our goal is to factor this volume expression into 3 factors that can represent length, width, and height. So let's begin. So the first step we're going to do is I'm going to help you guys motivate a theorem that you guys can use when we have a situation like this, and the leading coefficient is is um, it's not one. I'm thinking I might just do it. Just do it on this page. Yeah, I might just do it on this page. I think I just have room. So if we really think about what were to happen if I was to factor all this stuff out, what has to be true, since the leading coefficient is 3, what has to be true is that one of the factors has to have a 3 as the leading coefficient. One of the factors must look like this: 3x minus some number b. This has to be true. If you're going to get 3x cubed out front, it's got to be true. What also has to be true is if you were to expand all this out, if you were to like take your final factor expression, this is 3x minus b. If you were to expand everything out, that number b has to go in to 2. Otherwise, it would be impossible to expand this out and get 2. This b has to be a factor of 2. B must be a factor of 2. And from what we know earlier, using the factor theorem, that if we take that, I guess this would be v and not p, for our example here. If we put in b over 3, we have to get 0. So if one of the factors has got to look like that, and where b has to be a number that goes into 2. So like positive 1 or negative 1, or positive 2 or negative 2. So this brings us to the rational zero theorem. And it says this: so if you have a polynomial with integer coefficients, then x equals b over a is the zero of that polynomial, where a and b are integers. A can't be 0 because you can't divide by 0. You know, for any possible 0, this has to be true, guys. The top number, the numerator of that rational 0, has to be a factor of the constant term. The denominator of the leading of that 0 has to be a factor of the leading coefficient, and you know that ax minus b is a factor of that polynomial from the factor theorem. So if we go back and look at our example, I think we'll just go to the solution here. If we apply this rational zero theorem, what we're looking for roots of the form. I'll just write this out. We want zeros of the form b over a. And I just want to actually mention too, we're going to solve this one using technology. We've got a lot of experience now, examples solving with division. We're just going to get this one wrapped up using technology. So what do we know? We know b must be a factor of 2. Which means that b can be positive or negative 1 or positive or negative 2. We know that a must be a factor of the leading coefficient, 3. So a can be positive or negative 1 or positive or negative 3. Any 0 of this function is going to be a combination of these guys. So what do we have to check? So possible zeros. So we just kind of run through all the combinations. It could be plus or minus 1 over 1 or 1 over 3, 1 over 1 or 1 over 3, or positive or negative 2 over 1 and 2 over 3. All the combinations. That should be plus or minus. That should be plus or minus 2 over 1 or plus or minus 2 over 3. And just simplifying these 1 over 1. So our possibilities, positive or negative 1, positive or negative a third, positive or negative 2, positive or negative 2/3. That's it. Those are the only 8 possibilities, guys. And let's whip out Desmos and let's see which ones are zeros so that we can factor this expression. So let's bring back Desmos. Let's pop in our new polynomial. This one is v. So v of x was 3x cubed plus 2x squared minus 7x plus 2. We'll add a table, checking values of the volume at x1. And what were our possibilities? Negative 1, 1, negative 2 and 2, negative a third and a third, or 2/3 and negative 2/3. We're expecting 3 factors, and we've got them. Look, guys, 1 is one of our zeros. Negative 2 is as well, and 1/3 is also. So let's get these results back in our note, talk about what factors these values correspond to, and then we'll wrap the question up. So we saw that v at 1, v at 2, and v at a third all gave 0. What the factor theorem says, that means that x minus 1, x minus 2, and, so be careful with this last one, what does this root of 1/3 correspond to? Corresponds to a factor of 3x minus 1, right? 1/3 makes that 0. Our factors. And so our volume function can just be written as x minus 1, x minus 2, and 3x minus 1. Pretty cool. So please, when you guys are factoring an expression with a leading coefficient like this one, that's 3, you have to use this rule using the rational zero theorem. Think about what the numerator could be. It's a factor of the constant term. Think about the denominator. It's a factor of the leading coefficient. Think of all the combinations. Those are the values that you can try. We solved this one using technology, but of course, once we found that x minus 1 was a factor, we could have used division, got the remaining polynomial, and used division again, or some other factoring method. All right, that's actually A. So our possible dimensions are, well, these are our possible dimensions. So we've wrapped up A. I think we can just do B in the space I have here. So when x equals to 1.5, then x minus 1 equals 1.5 minus 1 is 0.5, and we're in centimeters here. X minus 2 is I think, oh my, yeah, it's minus 2. Okay. I was thinking I'm going to get a negative value. It's okay, easy fix. So sorry that you were probably wondering when I would catch my mistake there, but that was minus 2, meaning x plus 2 is a factor, x plus 2. Okay, and this will work. So the second possible dimension is 3.5 centimeters, and the final one, 3x minus 1. 3 times 1.5 minus 1, 4.5 minus 1, also 3.5 centimeters. All right. So good stuff, guys. You're doing a great job. We've done a lot in the last 2 lessons, but now moving forward for the rest of the unit, we'll have these skills. Our divisions will be quicker. We'll make use of technology to factor larger polynomials very quickly. So that's what we're doing next. Next, we're going to apply our new techniques to solve higher degree polynomial equations. And the method we will use to do that is factoring. And we now have, on top of all the methods you learned in grade 10, we now have the factor theorem to help us factor larger degree polynomials. So I've got some suggested practice for you guys to work on. It's a lot, and I just want to, you've heard me say this, but you guys are senior students. Many of you guys have jobs or have clubs, and when you need to practice. If this made a lot of sense to you and you can rock it out and feel very comfortable, then try like one or two from each question, right? Just try a little bit. If you look at a question and you say, well, I know how to do that, I'm feeling good about that, I don't really feel I need to do that question, that's okay. Do as much as you need to. So some of you guys might not need to do much, but some of you guys are going to need to practice a lot in order to get better. And yeah, part of just being a grade 12 student is, finding that balance and, being self-aware enough to know how much you need to practice. I would suggest doing all of it, like just making sure, but again, like, if you're feeling comfortable, then that's going to get repetitive. So just do what you need to feel comfortable. All right. So yeah, rant over, practice as much as you need to. In our next lesson, we're going to solve higher degree polynomial equations, but the heavy lifting is done. We'll be able just to solve polynomial equations quicker by factoring. And I'll start having some short quizzes and assignments popping up as well into Brightspace. But yeah, guys, stay well, take care,